Okay, so let's go with the first example of the Couette flow. So Couette flow is as we discussed, this is the wall-driven flow. So let me explain the situation. We have a wall, and then this wall is moving at the constant speed of the u, for example. Okay, and then this moving wall is at the constant distance from the stationary wall. Yeah. Okay. So this is in the top is the moving wall, and then at the bottom is the stationary wall. So in this particular situation, between these walls are fields with the fluid with the viscosity mu. Okay. So and then let's just set the coordinate here. In this case, okay, let's just call this is the we call this is the I mean we can actually set it in whatever way. But if you remember the week one, we set this is the y-axis, and then this at the bottom we set the y equals to 0, and then this particular distance between two walls the h. Okay, so so if you recall, right, this is something that we discussed in the week one, and then discussion, if you remember, is the fluid particles between these two walls. Okay, and then this is they are going to create the linear velocity gradient. So I'm not sure if you remember the discussion we had. So at the time of the week one, I sort of imposed, oh, this is the results of the this flow. But we have never have proven this. Okay. So today we would like to use Navier-Stokes equation that in fact this is the solution that we are getting. Okay. So with this, okay, just recall here, in the week one, what we had here is we assumed linear velocity gradient. Okay, what that means? It means this is let's say this du dy, how u is going to vary with respect to y, which is in the vertical distance, the distance between the wall. So this is nothing but this capital U, which is the speed of the moving wall divided by h. Okay, this was really the assumption here. And then what we had as argument here is because this tau shear stress is given as d by d viscosity equation. This is d tau equals to du dy, and then this is going to be nothing but mu times u over h. Okay, so this was the argument that we had in the week one. Okay, okay. So really, what we are going to do now is okay. We are going to prove this. Okay. That's the Couette flow. Indeed, have the linear velocity gradient. Okay, so this is really by the end of this, this discussion, we are able to prove the actual velocity profile of the Couette flow. Okay, so let's carry on. Okay, so the objective again is the solving Navier-Stokes equation for the Couette flow. And then, in fact, this is really the the good example because if you remember, Couette flow is very, very simple, right? Okay, yeah, that is but even with this, very simple, the geometry, it's end up, the solving differential equation is a bit more, bit cumbersome. Okay, so let's just do step by step. Okay, so first step here is the okay. Let's describe the flow and then let's postulate the solution. Okay, so what we have here is the okay. We are going to have this wall. I'm going to draw this in the slightly in a three-dimensional matter. Okay, this is the wall that is going to move from left to right. Okay, and then we do have some kind of the stationary wall. Okay, so this is the stationary wall. Okay, so and then the what we can do here is the to do this kind of stuff we always consider the coordinate. Okay, so we are going to set the direction of the wall is the x, and then the distance, in the direction of the vertical distance between the wall, we call it the y, and then z is the towards the out of the page. Okay, so and then what we have here is the this velocity. Of course, it's going to be u of the I plus v of the j plus w of the ek. Right. So now we would like to make some kind of observation. We would like to consider what u, v, w look like. Okay. We postulate what u, v, w are like by observation. Okay, so this is really the key of the solving Navier-Stokes equation. So let me try to explain what it means. Okay, so we are going to have okay. Let's try to draw. This is the fluid particle here. Okay, so now what we want to know here is the this fluid particle to which direction do they have a flow? Okay, so this is the let's say this is going to be u, right? And then this okay, b is the distance between the wall, so let's call this is the b, and then w is the in plane, okay, in parallel to the plane. So in this case, okay, if you take a look at this fluid particle, essentially we would like to identify which is the direction of the fluid this is moving. Okay, so let's see the following. So let's okay, so first one is a U. Okay, the of course the okay the idea of the U is there. Okay, it's already we discussed. But when the wall is moving, there is a shear stress, and then this shear stress is going to pull the fluid particle in the x direction. Therefore, it is very safe to assume that the U is not zero. Okay, this is the moving in the x direction. Okay, I think this is probably fair. However, what about the V? V is the when you are going to pull this wall, and then the bottom part is a stationary wall. In this case, is there any motion of the fluid particle which is getting closer to the either of the plate? Does it move up or down? And then if you think twice, right, we can actually consider there shouldn't be any flow, which is going to, the fluid particle is not moving upward or downward. Therefore, we are able to say V is equals to 0. Okay, this is the no motion in the y direction. Okay. Lastly, what about the z? Okay, or w? W is also, W is is this fluid particle is coming out of the plane or flowing in the plane, which is unlikely to happen because the motion of the wall is the only moving towards the x direction. So W is probably also equal to 0. Okay, so this is also the no motion in the x, y, z direction. Okay. So here's the here's our assumption here. All right. So that's really good. So originally we thought this velocity equals to u I plus vj plus wk. But this our assumption here or our observation really suggests this probably this one equals to 0, v equals to 0, and then w equal to 0. So this, the potential velocity has been a lot more simplified. Okay, this is going to be u of the I. Okay, so in general, okay, let's just take a one argument ahead. Okay, so now we said the velocity is only has a u component, x component. So now second things we want to think about is the which variable does u depend on? Okay, this is really a important question to think about. Okay, now in general, right, this u can be you have potentially four variables, okay, x, y, z, and t. Okay, so this is really, I mean, this is a four sets, right? But we are making a few different observations here. Once again, okay. So first things we can do here is okay. Let's just assume, okay, assume that the flow reach a steady state. Okay, so in this case, this is going to tell you there is the no t dependence. Okay, right. So that's the first thing. Okay. The second thing, is the two different, okay, maybe you can take a look at this, the particular drawing. Okay. So does u depends on the where this is located along the x-axis. Once they reach the steady state, it is probably unlikely that the u is not, going to depend on the along the x-axis. What it means here is the okay. So if this particle is the this is the along the x-axis, right? Okay. So once they really reaches the the steady state, each fluid particle should have the same fluid, right? Okay, same velocity. Okay, so perhaps with a bit more space we can draw here. So if you have this fluid particle here and this fluid particle here, this fluid particle here, okay? So these three fluid particle, okay, let's say they may eventually achieve the speed of the U, right? But this in fact, these three fluids should be moving at the same speed. Okay, so this is the fluid particles moves at the same rate. Okay, at the same speed along the x. Okay, so this is the another things you can say is the no x dependence. Okay, and then lastly, one thing that you could say here is the what about the y. Okay, so we can just go one by one, but okay, let's just go with the z. Okay, this is the direction of the z. So if you take a look at this, those fluid particle, okay, in fact, as long as you are aligned at the same level, okay, or same plane, same xy plane, right, the location of the z also shouldn't matter. Okay, so the same things. Fluid particle moves at the same speed along x also and z. Okay, and then this is also going to tell no z dependence. Okay. However, what about the y? Okay. In this case, if you take a look at the y direction is the distance between these two walls. Okay. So this is DE, Y. Okay, so if you take a look at this, the different fluid particle, as we, can sort of, anticipate that's, if you are closer to the bottom wall, which is stationary, they don't move a lot, right? But, if you are closer to the top wall, they are moving much faster. So we don't know the actual the velocity profile at this point, but the fluid particles moves at different speed. Okay, between two walls. Okay, so really it depends on the y. Okay, so it's y dependence. Okay, so this is really good. In fact, this argument really tells you, you originally we thought u equals to x, y, z, and t. Okay, and then but however, this argument really tells you it doesn't depend on x. It does not depend on the x. Also, it doesn't depend on the z, and then it doesn't depend on the et if we assume the steady state. So what we have left here is the following. It's going to be nothing but u of the y. Okay. So in fact, at this point we don't know. Okay. At this point we don't know. But this is the u equals to u of the y, and then this is really the postulated solution. Okay. Okay, and then actually, in addition to this, okay, in addition to this, we have two more postulate, which is going to be v equals to 0 and w equals to 0. So also these are the also another two sets of the postulated solution. Okay, if you want to combine them together. Okay, so So this is really the we have postulated the solution now. Okay. So that really concludes the first step. Okay. First step, just to recap here. First step is the based on the geometry that we have. Okay. Based on the geometry that we have, we would like to consider how this flow looks like. At this point, we all we want to say here is the which component is equal to zero, which component is non-zero. And then in addition, for non-zero component, which variable does it depends on? This is something we would like to, think about through this postulate. Okay, so this argument here really tells you, the U only depends on the distance between these two walls, where it is located between those two walls, right? So U equals to U of the Y, and in addition to this, there is no the Y component flow and then Z component flow. So the V equal to 0 and W equal to 0. Okay. So this is the after doing the postulate. Okay. Right. So if this is all right, okay, let's just okay, go to the second part. Okay. So second part we want to do here is the we would like to check. Okay. We would like to check if the postulated solution if the postulated solution satisfies the continuity equation, which is the in this case, okay, for the steady flow. So we made a steady flow assumption. Steady flow assumption. This is the so continuity equation is the okay. Let's say continuity equation is the 0 equals to nabla dot rho times v. Okay, this is the continuity equation. Okay, so let's try to check if our solution, postulated solution, really satisfies this. Okay, so this is the let's say right hand side of the continuity equation is the this nabla uh, dot rho v. Okay, and then let's write this explicitly. This has three components. Okay, this dx of dE rho u plus dy of dE rho v plus ddz of dE rho w. Okay, and then we do have the postulate solution. Let me write it here once again. Okay, which is the u equals to u of the y, v equals to 0, and w equals to 0. Right, so let's try to plug them in. Okay, so in this case, okay, first part is the indeed what it happens here is the ddx of the rho times u y plus okay ddy of the 0 plus dd0 or ddz of the e0. Okay, so without any ambiguity, the second and the third term is the this one equals to 0, this one equals to 0. And then first term also, right? I mean, as you can see, u is the function that only depends on y. So if you take a partial derivative with respect to x, then they also disappear. Okay, so this is really nice. In fact, this is the e equals to 0, which is the e left-hand side. Okay. So this is great. So this is really telling you the conclusion that we can draw here is the postulated solution satisfies the continuity equation. Okay, so this is really a good news. Okay, so now we don't know the solution yet, but at least that we can say this is a good candidate to analyze further. Okay, so with this, right? Okay, now let's try to simplify the Navier-Stokes equation in the next step.